Oh, okay. So, Professor John Baras. He's a distinguished university professor holding the Lockheed Martin Chair in Systems Engineering and a permanent joint appointment in the Institute of Systems Research and EC Department at University of Maryland, College Park. He received his PhD in Applied Math from Harvard University in 1973, and he has been with UMD since then. His research interests include systems control, optimization, autonomy, machine learning, AI, and a plethora of research interests. He has been awarded 20 patents and honored with many awards as innovator and the leader of economic development.
Okay.
Maybe I can ask Professor
Just
Shankar.
add, it's a great pleasure to have a friend from so many years. Don't worry, we won't detract from any of the time you need for your talk, but it's a great pleasure to have you. But let me, there's also a reason. I also want to plug the fact that he will be giving one more talk on Thursday at 1 p.m. in the C3DTI Symposium. So please stay tuned. The announcements will go out tomorrow, and Dr. Manchivu will be his host. John, it's a great privilege to have you. Thank you.
Thank you. So it's good to be here again. The first time I came here was 74. Most of you were not born at that time. This fellow was not even a student then. Okay, so anyway, so happy to be here. I want to talk about the topic that we have been working on for several years now. For us, trusted autonomy is essential. You cannot talk about autonomy without talking about trusted autonomy. So we'll see what this means for us. These are some of my collaborators. Some of them are students that have left, and there are a couple of faculty like Yannis Alimanos and Cornelia Fernuller and Rance Cleveland. The rest are students. Some of them are with us. Others have gone. Chavo, for instance, is in Michigan State, and you know some of his names. These are the fundings. Okay, so I don't think I need to tell this group why autonomy and trusted autonomy is important. There are some examples here from fueling aircraft, from cars. This is some work we have done in Belize, going with UAVs to try to sense in agricultural applications what's going on with diseases and try to see what to do. The other is disaster relief. We also work a lot on the fundamental problem of teaching robot tasks. We have a way to do it we think is more robust. And in this context, of course, human-robot collaboration is very important. And one of the issues that I talk a little bit about is what do you mean by teaching and how do you do it in such a way so that you can teach in one environment and transfer it to another easily, and you can teach one robot and transfer it to another, like you do with humans, okay? And there are some nice pictures about collaborative robotics, both from commercial and military. And for those of you who are in networks, this is also applicable to current communication networks, like especially 5G, 6G, and next generation, because the new topic in networking is autonomy. You try to do the management of networks autonomously, and that should be very, very good news for control people, because everything now has become software control, thanks to software-defined networks, network function virtualization, and the like. In a simple language, we are making the entire network virtual, and everything that you do is actually a control problem. You don't worry about the hardware anymore. This is thanks to Newt McCune, who did it for core networks, and now we're extending it to 5G, and there's some very interesting problems there. That's why I put that slide there. So the key challenges are, safety, of course, is very important for trust autonomy, and what can be learned. And you all know from your student days that you don't learn if you don't make mistakes, right? If everything goes rosy, you don't learn much. So one of the issues is, can you actually push the system to the limit of learning, but not faulting? And that trade-off, in my opinion, has not been understood, it has not been studied a lot, about how do you learn more by pushing the system to the learning and then learn and go on. And then human-machine collaboration is very important, all right? And how is it safe? I saw this picture of myself having Baxter giving me a coffee, which is fake. We have tried 1,000 experiments because the coffee can be hot. And with a couple of students of mine, we're trying to make this now real so that it actually works. And there are physical limitations, but how fast you can do that, how fast you can learn, how fast you can work. In other words, timing here is very important. And one of the unsolved problems in robustness is robustness with respect to time and space specifications, especially the time issue. I'll show you some simple steps we've done on that. Okay. So there are several methods. You can do autonomy for single or multiple systems. We have done all the work on artificial potentials with Shabotan and others. There's, of course, the work on reachable sets and appropriate verification, the barrier functions that we do here, also with reachable sets, and controlled synthesis using optimization, including logical constraints that they lead you to mixing the programming. And if you are into model checking, actually, you can do that with model checking like UPAL and so on and so forth. And I'll touch on to these things, okay? So let's go to the old work. You have a bunch of robots, and they try to go to the target. They try to avoid the obstacle. The selection of the obstacle to have a cast is special. You will see why. Because the robots are going to get caught there. Okay. So you try to do the old approach where I do potentials and combine them, like you see here, with different coefficients. They sum up to 1. And you have a target potential that attracts you. You have potentials that try to repel what's each from each other. And you have objects that try to repel you away, and so on and so forth. The problem, of course, with these methods that even if each of the potential functions is convex, the combination is not convex. So you get into local minima and all kinds of problems. So what's the answer that we did is they all say that the optimization we always use, be wise, randomize. Okay, so we randomize the problem instead of doing the gradient minimization. Instead of minimizing v, we did maximize e to the minus v. So you go into large deviations and these problems. And you get them to randomize algorithms. The penalty we pay, of course, now is that your constraints are going to have some probability of being violated. But we saw with Chabot that this leads to path optimal solutions. Okay? And I'll show you with pictures. It's a remarkably simple theory. So this is what happens even when you have sentries. And this is what happens if you don't do anything clever. On the right-hand side, let's see if I can do that. Yeah, see, they get stuck there. Okay, if you do just straight gradient, you know all that. So we now think of the agents being on a square grid. So this becomes a Markov, a Gibbs field. All right. So then I can move around with the potentials that you see on the right-hand side. And I'm exploiting the fact that I have a Gibbs distribution. And basically, I move around by throwing dice that they are loaded according. Remember, I told you minimize V, maximize it to minus V. V has a sum like that, so it depends on these local potentials. Okay, so this works pretty well. And this is inspired by similar methods in image processing. We have the name Gibbs Sampling, all right? So it's the same idea. This is old work. There are 2 papers in Automatica, and you see what happens. You go to one place, you want to go somewhere else, you create possibilities, you throw your dice, and you move, okay? Statistically, all right? And there's a very good analysis of that on these papers, and you see what happens. Now you don't get stuck, but you pay price. The price is that this is slow because they keep searching. So you don't do exploration, you do just exploration, and that's too slow. So we did a mixed method where you do exploitation for a while, and then you exploration. But we still don't have a method where you switch from exploitation to exploration automatically. We just put it in, okay? So the simplest example is I tell you there's a very nice restaurant downtown in San Francisco. You use your map, you go in the area, you don't see the restaurant, you start looking around, okay? That's a very simple example. Now, these methods are extremely simple, and you can make the collective to do all kinds of things, like 8 figures and so on and so forth, lines, by very simple potentials. I'll show you some here because that's old work. We are revisiting for various reasons. Let me see. Okay, that's the rendezvous point where you tell them what to rendezvous, and the other one you tell them just get together, and you see what happens. The first cluster in groups, and then the groups cluster. And there are various things we're looking at. Then you can make them do 1 line, 2 lines, 3 lines. Okay, things like that with very simple potentials.
Yeah, here's the dynamic crash while doing that. Right?
Yeah, because you put this pairwise potentials, okay? Yeah. So the remarkable thing here is not that. This we expected. The remarkable thing is that we proved that in the thesis of Wake C, who is with the company here in California, and then people at the U proved the same thing, that the methods are very robust to the functional form of the potentials as long as the functional form is the right qualitative characteristic. Okay, so as long as the potential is like that, if you want to keep people away or like that, the actual functional form doesn't matter, which means the following, that I can actually fit arbitrary functions with very simple measurements. So some people have done like measuring just the distance and then fitting an appropriate distribution and then running it, okay? And even more so, you can actually take the gradient and interpret it as even simpler. So because we work on another project, try to recover the collaboration laws of ensembles in recent work with DARPA and Park from birds and UAVs and so on and so forth. We saw that there's no uniqueness in this construction, but this is not weakness, it's actually robustness. Because if you have many potentials that they give you the same trajectories, you now can ask yourself, what is the simplest form that I can, okay, so that's kind of thing that, so that's one method, okay? The second method is the one you know about reachability analysis in terms of constructing tubes and then following these tubes of the nonlinear system. Here we use the zonotopes of Matthias Hartog from Munich, but you can do others. You can use ellipsoidals. Essentially, you look at the tube and you take slices and you try to project it. The more recent work we are doing here in this area is try to essentially get inspired for the modern cars that you see. You have a big screen, your modern car, you see a tube in front or back when you park. This is actually a tube. So we try to do it faster and try to use it as a method to drive the car or many cars and so on and so forth. And you'll see this later. There's still a very active work in this area, try to make these computations fast because currently it's not. So here we're trying to do things that you all know, try to go and calculate these reachable tubes from two aircraft in such a way so that they avoid each other and they allow maximal set of controls that they satisfy these tolerances. So you can, if you find that first, then you can actually find the controller so that you do optimal time and so on and so forth. Okay, so there have been many approaches to that problem. Now I get to more recent work that we've done with several students where you try to do path planning. So here path planning means I want to go from A, stay there for a while, go to B, stay there for a while, go to C. This arrow here is a moving obstacle. Okay. So we don't use LPL because LPL is not realistic. We use MTL, metric temporal logic or metric interval temporal logic for the simple reason that my constraint is I want to go through this door in 10 minutes plus or minus 2 seconds, and I want to allow some tolerance from the border of the door, like 10 centimeters, okay? So it's finite time constraints you have, not I want to go eventually to the door. And this is captured by MITL. Of course, the difficulty is that even in MITL, you don't get all the time which automata for some subclass you get. So the problem is a bit more difficult because definitely for metric temporal logic, you don't get for which automata all the time. But we use an old method that I think was done at Caltech and other places where you take the logical constraints and you can turn them into integer constraints. Okay, so here you see an MITL formula, okay? And then you can turn this, you have say this optimization problem, I want to minimize the cost, subject dynamics and some logical formula. You take the logical formula and you can solve, I think some people call this the big M method, that all the constraints you have can be done, can be turned into convex constraints, but integer variables. So you end up with this kind of problem, right? So that's one example that this constraint is satisfied by this integer constraint, okay? And Richard Newey and others have done this many years ago. We use it, and now the problem becomes very quickly this. Okay, so I have a mixed integer programming problem. That's bad news, because many of the mixed integer programming problems are not scalable. So the answer that we give to that is divide and conquer. We use the fact that the logic problems can be decomposed, and I'll show you examples of this later on. So therefore, if we have 10 UAVs with these logical constraints, we subdivide to logical and optimal control problems for each UAV and then compose them back. Okay, so that's an important property of composability in these problems, and it's not well understood because when you decompose constraints, okay, you can solve the problem, but then when you put them back, how do you combine the constraints so that you're okay? What you have to do is you make them more conservative, but you have to calculate that. So you can save, you can give some assurance for autonomy. Otherwise, the whole notion of trust autonomy doesn't make any sense. Okay, so here's an example that says that I have to go to for a certain interval to A, and then I go to B, and then to C in a certain order. I have moving obstacles, and you do this formulation for small number of problems work very well and very fast, and you get this kind of complicated trajectories, right? So these problems are not simple, but you can solve them, all right? And other people have done similar things. So now I go to the other side of things of using model checking to do this kind of planning, right? And the one, so here you have an MITL specification about grasping an object and then moving it and so on and so forth. Okay, so we used UPAL, which is a public domain model checker for timed automata. Timed automaton is an automaton where the functions are the states, but you move from one state to the other if you satisfy certain guarantees and some timing constraints, all right? So that's an extension of automata. And they describe very well sequence of actions, okay, with various constraints. So, for instance, on the right-hand side, you see there's a timed automaton characterizing the movement, okay, the location states. And on the other side, I have the action states, like I move, I hold, I grasp, and so on and so forth. Both of these things are time automaton. Okay? And then I can put this into a model checker and find out if there is a possibility to find a path to execute this with certain constraints. Okay? And you get this model checker in UPAL for this problem where this robot is trying to grab something from the left-hand side, go over the object, and put it over there. Okay? And the model checker, as you know, if you know model checking, not only will tell you whether it is possible, it may provide a counter example, or it will give you a fix. Okay? That's why we like them. You get these kinds of answers for the path. And if you can do this on your head, I'll give you a big prize. Okay? That's so that you get another alternative of doing the same problem by using these model checkers. Okay? And then the interesting thing here that we do with my students and we live with now at Google is that if you have such a model, all right, you can actually create a hybrid automaton like you see here, again, of the time automaton type, but now you can build a automatic monitor of the automaton to see, and that monitor is an analog, if you like, of an observer from systems, right? This logical system, which you build automatically again, it monitors the execution of this task, and it can alert you if things are not going properly and so on and so forth, right? So, for instance, here you see this monitor, very simple. It checks whether some state is bad state, or some of them are alarming, or some of them are good states. You can use this automatically synthesized monitors for monitoring, or also as a base for reinforcement learning later on, if you want, with these hybrids. Okay, so that's another method. And then we come to the first step that came from here, from Sessia, right? Single temporal logic, where you try to go towards robustness in time and space. And here, the single temporal logic, if you look at these events, the difference is with what values of x the constraint is satisfied or not. Okay, so it's a first step towards this time and space synthesis, and you can actually put this together and even understand problems like this, where you have nonlinear dynamics and you have an STL fragment of the constraints, like I have here, and then you can use this to actually get event trigger control in the sense that the triggering is when something is not as planned. Okay. So when we say trusted autonomy, in the most general sense, in our work, we mean that the task execution is not as expected or as planned. Something is not going right. And that can be because the environment changed, is because the model that you have changed, or because the way you're doing it is not right. And you have to figure all that out. So we call this self-monitoring. Then you have to self-learn, and then you have to self-adjust. And if you think about autonomous systems, they must have these properties, okay, which we all do as humans and other systems which are higher level. And here's an example of this STL where I have three UAVs that they have to go in the direction up there with various specifications that I have. and I'm trying to get some robustness, we solve this problem and you see that they go and the raw functions give you the robustness with respect to x and so on and so forth. So that's another useful tool. But quite a few people now have done quite a lot of work on using SDL and even have gone to the problem where they try to do robustness. Okay, so now I'm going to go to some more advanced work where we follow this divide and conquer. Okay, and the key problem here is composability. How can you take these systems that they involve automatic control and logic, decompose them, and then put them back together and prove that they do the function? Okay, so that's commercial. So what we do is we have trajectory planning, and we have all this temporal logic thing, and then we basically divide that into the problems for each UAV. So, okay, so here is an example. I have several UAVs. I try to go to this window over there, go on the other side of the wall, pick up something, or save somebody. Okay, and they have to cooperate. And the lower part is work with done with ADB, which uses UAV to go inside the factory and look for leaks or faults like this. Okay, similar kinds of problems. Okay.
Is there any question on Zoom?
Is that?
I heard some voice, so I'm just confirming.
They can either put on the chat, you can read it, or you can.
Yeah, please feel free to ask questions or put it on chat. I'll read it.
Okay, so in the search and rescue, there's this problem. Of course, safety is both with respect to passing through the window with some space tolerances, but there are multiple problems. So suppose the UAV goes through the window and find out that they cannot fly through the window that way, it has to do that. And it calculates it doesn't have time to do that. So what we do in more recent work is the first UAV tells the second UAV that it has to do that, goes around, this one turns, goes through, and the other one comes back. So it's much more complicated, so like logic. You can do all these kind of problems. So this is the model. Okay, so now you have them, you exploit the atomic propositions in this logic, and you take the statement you have on the left, for MTL, right? And you use the semantics and you decompose the global logical constraints to individual constraints, okay? So that's the constraint we have on the bottom. And these go then various constraints for each of the UAVs. And I think this is coming up. Yeah. Okay, so in the system dynamics is a hybrid model that shows you the various functions of the UAV. I take off, I land, I steer, and so on and so forth, grab. You have the classical model of the UAV, okay, which many people are using. And then you have the Baras model over here. And you take the object, you put them together, you have identified the automaton. Okay, and every UAV can satisfy that. So here is the mission. I write a formula down for the metric temporal logic. Okay, every time you see these subindex of intervals, that's the difference between LPL and MPL. And you have to find the object location. Then you go to the save location, so on and so forth. And for instance, for quarter of the Q1, the corresponding mission looks like this. And you can have this problem where for each UAV, you see there's an I there, you have an optimization, there its dynamics, and the logic for that UAV. Okay, so I decompose the big problem using the decomposition of the logic to subtasks for each UAV, solve the corresponding problems, right? With several papers that we have on that, and then you put them back together. So given an MITL specification, there are the compositions for each of the UAVs, and then I can solve this problem and put it back together. There are things you have to choose here, including the time horizons for the sub-problems and then how to put them together. Okay, so we do the same formula. Okay, we term the MTL specifications for each UAV to these integer constraints. So we end up with a large mixed integer programming problem to several smaller ones. We solve them, we put them together, and then it works, right? That's this approach. Okay. These are the subtask formulations.
How do you choose the standard for the subtask? So there are some like
the times in particular. These
Yeah.
are not much else. The other things come from the decomposition of the mission for everybody, the mission of everybody, right? So for instance, if I have two EAVs, who comes first? Right, so I have to specify that in divider concept because not both of them go to the window. Things
Can
like
you
that.
just do that manually?
You try.
Okay.
If the problems are small, you can try different options. Usually, it can be done online by seeing who is the closest one. Okay. For instance, in the example I show you, where it has to turn, this guy's going to go away. So the other one's going to go first. If it can go first himself, he goes first himself, and he decides that by some measuring the time to crash versus the projected tube, and then he decides that it can go through and goes through. Okay, so the key idea here is that I take a large problem, decompose it, solve it, and put it back together. And in the example we have done, even in laptops, this can be solved pretty quickly. Okay, when we use this kind of tools that everybody knows, right? Right. So the overall, of course, is not optimal anymore. You have some optimality, but you cannot go for the optimal because of the computational complexity of larger mixing as a programming problem. All right. And so the key idea here is that this way you get at least some scalability. Right. Here are some examples. I don't know if you can see them. So the computation is anywhere between 3 seconds and 10 seconds. Okay. So it's not that this is you show the decomposition here of the various subtasks for quadrotor 1, quadrotor 2. These are all expressions in MPL. And if you're interested in details, okay, it'd be better if you go to the papers and look at them. And we'll be happy to give you the software so you can reproduce our results. Nothing difficult here in terms of programming or computation, okay? And here is one, a bigger one, where we have, this is the paper for the older one from the last IPAD Congress, okay? Where we have several of these doing the problem. Okay, so and that's the other example we did for ADB for monitoring sign at the factory for problems. A production line is stuck, you have a leakage, you want to send somebody to inspect it and so on and so forth. Right, so these are similar kind of things. This is an actual factory that we did this for with ADB. It was about 2 summers ago. Again, same recipe. Okay, I have the quadrotor model. I have the various functions, ascend, cover, descend. This has the automaton. For each automaton, you have a nonlinear differential equation, as you all know. And you solve it. Okay. All right. So this is the temporal load specification corresponding to this problem. Sometimes here in these factories, you have to go to these places and spend more time. And you have the pipes and stuff like that. Try to find if there are problems there and so on and so forth. You can write those down. In MITL, it allows you to say, go there, stay for a few seconds, inspect it, zoom if you like with your camera, see if there's something more, and then tell me. Okay. We've done similar things for monitoring airports, for where you can go to the building and stay longer and so on and so forth. Again, some of the implementations, you see this is not a very special laptop, and you see the for each subtask is between 0.3 to 2.9 seconds. So this is definitely executable with not a lot of computation power. Okay, then a more interesting problem, which I won't give you that much, because I want to cover a lot of things. This is cooperative search and rescue, where there's a bunch of robots, there's a leader who has to go and avoid, and the others who follow him. Okay. So, and they have to go over there in the red square for the rescue. This is the team. Okay, and the red guy is the leader. And we decompose this into the functions of the overall team. Okay, and in each function we have optimization problems, which I skipped. There are papers on this you can look at, and that's the result of solving the navigation problem, the control problem, the sensing problem, where some of them are logical problems, other optimization problems. You put them together at the end, and you get this example where you see they avoid the obstacle, they follow each other, and they go towards the rescue, okay, in a coordinated fashion. Okay. All right. So this is a summary of this kind of work. Okay, now I'll go to something else, which is the first attempt we made to try to go after this robustness of time and space with my student Zheng Yu Lin. We're trying to do path planning. This is a very simple problem, but we wanted to have some robustness in time and space, okay, in the path planning. So we use STL. This is the same kind of example where if you change the X variable, one of these specifications in time may be violated more easily than another, which is the key idea in STL. All right, so here we looked at space and time tolerances in task planning. So the space robustness is how well a given signal satisfies a given formula. And the robustness degree is calculated causally according to these formulas. So basically, what these formulas are trying to do is two things. They try to find out how much tolerance given in space with respect to time. The way we calculated robustness with respect to time here, we put a Gaussian distribution around the proper time, and we allowed the time to be okay as long as you say 3 sigma from the mean, so forth. There are more recent work by us and other people that we try to do this robustness in time deterministically, not by stochastically. So what we did with NU is actually try to get this time robustness, as you see here, some tolerance with some distribution. And we were trying to calculate the robustness in time and robustness in space. What this means is how many controls as a set allow you to satisfy the robustness in time and in space. Why I'm interested in that? Because I may have other things to do with the controls, and I'm interested to have a reasonably large set of controls to satisfy the robustness, and then I can pick the controls from that set to do time optimality and other things, right? So we first find quickly which controls satisfy this robustness. Here we combine the set of robustness in time and the set of robustness in space by some two coefficients, and then we solve that control problem. And again, there are two papers on that, you can read that. But here are some examples. I have this kind of path planning, okay, for the optimization problem, right? And I'm trying to get the robustness this type. And then I'm also trying to say whether I can simplify the problem by using event trigger control and still maintain the robustness, okay? And we can do this by self-monitoring and self-corrections. And we do event trigger MPC, and you get this kind of results, right? I can maintain the robustness of the path where I activate my MPC control only in these very few instances. You can calculate these things, okay, in this problem. Or you can get a more difficult problem where you have things like that, where you get more. The problem is more complex now, okay? So you need to have more event trigger control. Essentially, the event triggering here is when you deviate from your planned trajectory and you are in risk on hitting stuff. Okay, and that hits. But this all comes from the theory. I think there's much more to do here, and I think we just scratched the surface of time and space robustness. It's a very important problem, okay? Okay, now I go to another piece of work that we're doing for many years with Jan Salimon and Miller, which was how to teach a robot to do things like making a sandwich, cooking an egg, cutting a piece of bread. But we did it by having the robot observe a human. Now, why is that the case? It's because we showed them, we believe first, and then we showed that this way the training of the robot is more robust than programming. Okay, and this a lot of people know. So in this context, you can, the robot can see you, okay, or you can see a video. And this example here in particular shows an instance where the robot was going over a plate, and we didn't want to go over the plate, so we grabbed the hand and say, okay, dummy, this is a better way to do it. And this was registered, one sample, and it improved later on because we told him that this was not very good, okay, instead of having him to learn. I want to stop here and give you a basic idea that we're working on, we have not yet completed. The idea is the following. I am trying to have the robot learn a logical description of the task. So Alimanos was using certain languages, I'm using time automata for this. So if I want to screw a screw, I have to do a time automaton. I have to take it, grab a screwdriver, put if it is Phillips or not, put it in the screw and start turning, okay, for the amount of time. Then the theory is that if I got the robot, sorry, this moves by itself. Anyway, you can leave it there. If I got the robot And I'm assuming two things. The robot has its own embodiment. It knows from previous motions in its computers how to move around. It also has its sensors. So I input into the computers the logical task and execute the path planning algorithm with these constraints. Right? And then it will find the path or it will not find the path. But we saw this for some of these examples. Actually, this was shown by DARPA in their showcase that they did in St. Louis about 5 or 6 years ago. Okay? This has the following advantages. If I have the logical task, I can go to another robot which has not been taught this, and it will execute again. Again, the robot will have different sensing, different embodiment, but it will have the same logical task plan. Or I can go to a different environment. Okay? Now, I usually am very truthful in talks, and I can tell you, we've done this, but when I checked the software, people were cheating at it. They were doing a little bit of patching by hand to make it work. Okay? And so we are re-examining now to make sure that this works the way I described it, that we just input the logical task, we use the sensor of the robot and the embodiment, and then the path planning works. And in this context, we did several things. For instance, we tried to understand how to characterize motions by finding various motion primitives and store them as atomic things, and how to combine them, and how do you do adaptation movement for planning to avoid obstacles, and also how to use attention mechanisms, the sensors, to try to focus the sensors on only things that matter. So that's basically the structure of our approach. It's what I would call more goal-oriented planning than anything else. And we have a long history on that with my colleagues there now and others. All right. So there's work here that has to do with attention. I'll skip it. Okay. Let me go on. Okay. You're going to hear more about that part we talk Thursday, because it touches on something that I have developed for many years. It's called model-based systems engineering. And it's very systematic and with languages and models and so on and so forth. And we try to embody all these ideas into this framework, because what's missing right now, and we've been asked to do that from many agencies. Here's the question. We have invested literally hundreds of millions of dollars in autonomy, and still we do not have an integrated tool suite that you can sit down and design a robot, including the materials and the geometry and all that, and test it, and then go make it. And what you make is very close to what you design. Keep in mind that this is happening in aircraft. 777, 787, and all these aircraft will be designed by this approach. You first do everything by this model-based system engineering that the source system and other companies are the experts, and then you go make the single screw. This has been going on in cars, but not yet successfully. And now everybody is asking for this approach to anything that we make. The reason being now because you can go from software to implementation by things like additive manufacturing and 3D this and so forth. Okay. So in Germany, there are labs that they can create very delicate medical instruments that go from the lab to the hospital by following the similar approach. So here, what we try to put into our system is the additions will come from automata, from autonomy, meaning the time automata, the specifications in MITL, STL, and then even contracts. Because you need to have a logical structure that is composable. And contracts, which is a technical description of assumed guarantee contracts, you have one of the experts here, and others on the one in Intelli, okay? We try to put this into the model system engineering, and we'll talk about this more Thursday. This is the slide that I captured what we have done in model-based system engineering. You basically have to integrate different models. And we use system modeling language, which is a modification of UML, which allows you to integrate physical models of all kinds. Sometimes you have to use meta modeling to capture them. All right. Then you link this integrated modeling tool with trade-off analysis, where you have to be able to handle both optimization and logic. Like, for instance, the log solver and complex, that Cflex that IBM has unified in their optimization sort of suite. And then you have this problem that is still open, that companies have been asking us, how do I find components that I designed many years ago, and they're represented in different ways, but they are similar to what I want, and take them out and put them into my modern design and so on and so forth. Now I'll tell you Thursday what the last 2 years have been trying to work on this model. Okay, so we have developed that a little bit further to try to go to autonomous systems, and the stack key is this, the requirements analysis. Meaning you write down various specifications, mathematically they will translate to constraints or metrics. For the programs we're talking about, they will have hybrid variables, they will be Boolean and numerical. And now you have a beautiful program how to verify these things. The methods are the same as the theory of analysis. And in our approach, we integrate everything from time automata, model checking, contracts, and even sometimes automatic theorem proving to try to get the specification of the requirements. Okay. And more about that. All right, I don't have a lot of time, but I'll show you this. All right, we wanted to find a simple example to show that this trusted autonomy is a useful concept. And by that, I mean, again, I can self-monitor, self-learn, and self-adjust. And I thought that the problem of picking a cup while you're pulling something and you prevent me from sleeping is a simple enough problem, right? And, I went around the world and they told me, I don't know what I'm talking about because this is not an easy problem, okay? Especially if you want to do it honestly, which means you don't pick a glass because then you can squeeze it and it's not going to slow, but you do it with the plastic, okay? Like that. Okay, so we did this with the shadow hand, which has too many sensors, but anyway, you sit on the left-hand side. And of course, the first thing that we immediately realized is that this is primarily a haptics problem, not so much a vision problem. The vision here is very little. Most of it is because you can do it blindfolded, okay, as a human. Even when I'm pulling something, because you feel the weight and you adjust your strength. So we did this. We measured the friction, rotation. We tried to also get some sense of the strength of the object we are grasping so that we can adjust, because we want to be as realistic as possible in the slippers. Okay, and we had some very good results. The controller seems to be very simple. And this is the plastic. I'll show you the movie, I guess. And here we did something else that's very important for model-based system engineering. It's called twin, digital twin. The digital twin is you make an accurate simulation model of the process. You use this type of manufacturing. This is going to everywhere. You use it to experiment, to design against, and when you're sure that you have something good, you go in and implement it. We did it here by doing very accurate simulation of this hand by using standard tools from simulation of robot hands and rods and so on and so forth. Let's see here what's happening. It's kind of slow. All right, so it won't be a lot of fun. I'm going to go through and show you the real movie. Here is the movie. So you can see it. If it plays. Yeah. Okay, so this is, there's no self-correction. So even with the glass, it slips. Then we adjust the hand. Actually, this hand is very bad design. Sometimes it gets stuck according to the location of the fingers. You can do nothing about it. And we're now looking at much cheaper grippers that they actually have full plastic fingers. You can do much better. This is the plastic stuff. And you notice that after it squeezes a certain time, it stops because it doesn't want to break the cup, right? It's mostly haptics. So that was my introduction to haptics, and I started learning haptics from my colleague in Germany, Sandra Fish, who's an expert on it. Okay. All right, so you can watch it because he has I'll leave the entire talk here. I'll go to something else. Okay, so suppose now you have some understanding of autonomy for a single agent. What do you do for multiple agents? Okay, and one problem I find here in the literature is that most people, when they talk about network control systems, they have this network on it, the bottom one, which is the communication network. In our work, we consider the collaboration network, which can be logical. I can collaborate with you, doesn't matter where you are, because we are in the same organization or other regions, okay? We have the communication network, which basically says who communicates with whom and what and when. And quite often you have a middle network that is the information network. So in the bottom layer, there are data. From the data, you extract models and other things, policies. Where do you store those? Right? So these multi-graphs, they have nodes. The point is that these networks do not coincide necessarily. And to me, the most interesting problem in multi-agent control is exactly to understand the impact of one of the topologies on the other. For instance, there's a well-known problem of if I'm doing consensus up here, what should be the network down here? And this started from simple consensus or regular graphs in the circle. And that's where the concept of shortcuts came over, the simulation. We proved this with my student Pedro and and so on and so forth. And that led us to discovery that the optimal topologies for communication multi-agent system is something that's called expander graphs, which are basically locally rich and globally sparse. And we now try to develop a metric of this, which is inspired, believe it or not, by how much copper you put down to make telephone lines that Bell Labs knew even before Pinsky came up with the concept of expander graphs, which has very deep connections with coding theory and ubiquitous code and all that. And the mathematicians in for advanced study in Princeton, they gave very nice properties. Expander graphs like fast diffusion, fast caching, very easy things that for us control people are very good. Okay? Anyway, here you find a litany of results that have done by playing the interface between the graphs. The most important one I want to point out to you is this. I already mentioned this. You know, there is this famous problem in control for many years that platooning is unstable, but it is unstable because people use this as communication graph near as neighbor. It's not realistic, okay? If whether you mean wireless communications or communication by sensing, it's impossible to restrict communications to near as neighbor. The moment you allow a little bit of neighbors, and we did it by a very simple expander graph with my student Anup Menon, who's now at the Google company that does the cars. What is it called? Waymo, right? The problem went away with beautiful stability results. Okay, just so that to show you how important it is to understand this trade-off between. Okay, now I have another talk here, but I'm going to go skip because this I added after the discussion in the afternoon with for cars. Okay, so one application of that is in autonomous vehicles problems. Okay, so that problem, these two problems are work of my current student Nilesh Yasasi, where we looked at merging. Okay, so I'm trying to merge. I have a flow here and a flow there, and I'm trying to do it nicely by interleaving and not slowing anyone. If you like to know, I mean, there is even a patent that Google has in this problem. It's an important problem for autonomous vehicles. We formulated as a centralized control problem, the dynamics of the cars, various parameters, okay, trying to show that you can interleave the cooperative control problem. And we have several results here with centralized control, decentralized not yet. This comes back to a question that Professor Sack was asking me about how you can group together the vehicle to try to see if you can coordinate a smaller group and then coordinate between the groups, which happens often in this problem. Anyway, these are some existing methods. You will see all that. I'm going to go to what we did. So what we introduced was heterogeneous traffic, right? Where we have different types of cars, different velocities, different speeds, and different priorities. Okay, so we solved the problem with more complexity than was done before. Okay, that paper got the best paper award in the Intelligent Transportation System conference, or whatever it's called. And the key idea here were these time sequences. So they are linked to distance to merge or time to merge and so on and so forth. And you try to estimate them and get a heuristic that gives you, right? Remember, when you drive, you look at the other guy and you're trying to go back and forth so that each of you go smoothly, okay? Unless you have a non-cooperative driver, which then the problem is more difficult. That's the workflow we have. You have the information collection, you have the priority assignment, you optimize the velocities, you get the sequence of times. This part is meant to be parallel. You put it together, you get the magic, and this is the paper that we did with several of my students. And then The velocity calculation is we use the quadratic control to make it simple. And right, this is robustness calculation because you calculate the timing so that you don't hit each other. So these are constraints in time. Okay, this was all deterministic. We didn't use potential fields or anything like that. Okay, and what we get is, I think there's a movie here. Yeah. And there's a version of that from multiple lanes. Then we did the performance analysis of this method with respect to others. And you get these kinds of, right, the speed that you get versus the blue method, so that you can go faster, which means you can get more throughput, the question we're asking before, and several other metrics, okay? Right. And here is multi-lane highway extension, right? Where you allow to get in, and this vehicle, you can go that way to make room for you, right? Not just one lane. Okay. All right. So the second problem, which is very interesting, is there's a lot of work on that through the years, okay, the last 5 years particularly. We tried to implant autonomous vehicles in a heavy traffic situation to diffuse congestion. And the congestion manifests in the traffic fluid flow as shock waves. Okay? So we did this work also with the references. So we tried to simulate the shock waves, and the key questions here is try to locate this autonomous vehicle so that you can sense the generation of shock wave as early as possible. Propagate backwards, and what this autonomous vehicle is supposed to do is try to slow down everybody so you don't get this congestion. Because once you get the congestion, what happens is everybody goes bumper to bumper and this goes backwards. It's called backward propagation shock wave phenomena we know for at least 50 years. All right, so you have to drive to model the humans here, very statistical in terms of velocity. There's a model due to Krauss, who has two parameters, okay, in terms of how people adjust their velocity and their reaction time. You have heterogeneity here. Some people are fast reactors, others slow reactors. Okay, and then this is the workflow. You have the traffic state estimation from each vehicle. Then you have some communication between the vehicles, which can be either direct or via the infrastructure or via sensing simply, which is called indirect communication. Then you have the detection of the shock wave in parallel, and then you control computation, and you go to the lower level control, and you, this is the other paper we did with Niles. Okay, so very simple ideas actually, but practical. And there is robustness here. I'll skip. This is the algorithm we have. I want to go to the simulation, right? Explain. Yeah. You see the vehicle? Right. This is with control and this without the control. Okay, you're going to see the way the software is being created, and then when you have this, it gets diluted. And the challenge now is, and you can see here how, if you use these things, model the position versus time, right? How the software gets diluted. Okay, which is the control. And the current challenge we're trying to do is, and then you have to ask, what happens if I have 2 vehicles, 4 vehicles, 5 vehicles, where I place them, okay? And what's the impact of this to the mitigation of the shock wave? And the last thing I have is this particular set of problems. We're trying to understand the following question. If you have vehicle-to-vehicle communication only, vehicle-to-vehicle communication and vehicle to infrastructure, and vehicle to infrastructure, and vehicle to satellite, each of them has different time scales. How much do you gain as far as optimality of the flow and all these problems, right? This is a problem that came as to both from both General Motors and Ford. Okay, then the different set of problems, okay, which I call complex traffic manipulation. You pass a car, you try to change lanes, okay? How do you do these things effectively, and what kind of problems you use, right? So very simply, you have to pay attention to your sensors and understand how much of that is valuable, how much not, and when. You have to do some sum, do navigation, to do actuation and control, and feedback. Okay? I'm not telling you anything that is not common sense. Then we studied several problems here. These are the key problems we studied. I'll talk very briefly about these two. Right? Passing a car in a road like this, when you have cars going that way and other cars that way, changing lanes in a movie highway, and I'm not going to talk about the other one. Again, there are papers on this. That's my student Faizan Tariq. I worked on this problem. So the car passing problem we've studied for several years, both here and our colleagues in Sweden. We have this logical model that we have to go over here and go around. We have 7 degrees of difficulty of this problem. The 0 one is you decide here you're going to execute this maneuver, you cannot change. And then you only have to do is calculate the accuracy of the velocity and acceleration of all the vehicles. And then calculate the probability of crash according to this accuracy. In this problem, we found that the most sensitive parameter is your ability to estimate the cooperativeness or not of this guy. Right? So trying to estimate real time, very simple variables, whether the fellow you're trying to pass and the fellow in second comes from the other is cooperating in this maneuver is key. Okay. And here is where some simple models of human behavior come in. I'll try to finish. This is work that has been done before on this problem, mostly by using optimization in these papers. We combine actually logical models and optimizers. So we did stochastic controllers with logical constraints, totally formal models in different papers. And the key, again, is this. The current sensors in the cars are very rich. So they allow you to reconstruct very easily what's happening around you, and you should exploit that. And then the controls become actually very simple. All right, so let me finish. What else I have? Sorry for skipping. Yeah, we have similar thing for various performance curves and so on and so forth on changing lanes. There's a comparison of the throughput and all that you can see. So I'm running out of time, so I'm going to skip this part. If you're interested, I can talk offline. Go to the final things I wanted to say. Sorry for that. Okay, this is it. So quite often I go to talks and people use the term AI. And I ask them, what do you mean by AI? And I can't tell them here an answer. This is what we mean today. Okay? So there are 3 challenges here. We are close to getting some reasonably universal architectures and mathematics for deep learning, where you actually control the complexity of the deep network. This is the work of my student Christos Mavridis, who just finished. He has done exceptional work in improving some areas of work I have done, where we basically did a learning algorithm, but with batch processing. He added to that real-time progressive learning, so you can actually start learning right away by adding to what I did before, something which is called deterministic annealing. And that actually solves the number of clusters you need, because it creates clusters as many as you need according to the data you have. Second one is you have to actually understand what's going on with this non-confinement architectures. Remember, there was neural networks that were called synaptic networks, where all the activity was in the synapse. And then computer science very cleverly did something that's called in-memory computation. So they showed that you can actually use this to actually do computation. The motivation for that in your brain is the same substance, and you do both memory and computation. So how come, right? So this led to several things like synaptic neural networks, neuromorphic machines, the loyalty type, and this hierarchical temporal memory architecture that people claim it learns faster and with less amount of data. These kind of neural networks are good for symbolic processing or concepts, and these are both for arithmetic. I say we need to unify the two. Then you would have a sort of a more universal machine learning architecture which can adjust itself according to what you want to learn. Challenge number 1. Challenge number 2. Okay. The big omission in what's being discussed in machine learning and AI is knowledge representation reasoning. Think about yourself. Okay, you learn. You don't let them in a database. You integrate them. You connect the concepts. You try to simplify them, and that is a condition for the next thing you learn. This is called knowledge representation reasoning. There are two fundamental models for that. The one is knowledge graphs, which also is called ontology in old stuff. And a more recent concept was this idea of semantic vector spaces that became big because of working natural language processing. And it is in the natural language processing and in general speech and sound processing that these two models of knowledge representation have been integrated. And quite a few people attribute the progress in speech, automatic translation, other things to this idea. Unfortunately, it has not happened in any other data field, this integration of knowledge graphs with semantic vector spaces. So this is challenge number 2. I was to create an integrated model. There are advantages for using this or using this, okay? Okay, and the last thing is to link this knowledge representation and reasoning with the universal machine learning, right? Then I give you the right to call the whatever you come up with AI. Because you will have the ability to learn, store, progress, condition, and so on and so forth, okay? And you can start proving things of what it can do and cannot do. I'm not saying this is the only way to do it, but at least in the work we are doing, we are trying to go along this path so that when somebody asks us what do we mean by AI, here is what we try to do. Okay. And with that, I think I'm finished.
A lot of different things. So I think we need to question a lot of you, these guys here, I have my questions. We need to study some of them.
What we're doing, what I'm going to talk about Thursday a lot is about this idea that